So we'll start today's session for computational science in engineering. So I hope you can see my screen. So Chandan, can you see my screen?
Yes, sir. Visible.
Okay. Okay. So we'll solve some questions today, and if you have any doubts, you can ask. So the first question is we have an ODE. The ODE is given, and use a step size of 0.3. The value of y at x equal to 0.9 using the Euler method is. So first of all, what is Euler method? So let's say this is x and this is y, and there is some function y equal to f of x. So at, let's say, x n location, the value of this function is okay, so we'll write g of x. So let's say this function is y equal to g of x, and what is given is dy by dx is equal to f of x is given. So let's say this function is given, which gives the slope of this curve at particular x location. So at xn, this function value is, let's say, g of xn, which is, let's say, yn, we'll say. So in Euler method, we approximate this curve by this by, by the tangent. For this, let's say we want to find this xn plus 1 location, what is the value of this y. So during this xn to xn plus 1, we will approximate linearly, and the slope of this line will be the derivative at this location. So derivative at this location is f of x xn, which is dy by dx at xn. So this is the derivative, and at this location we are finding the value of that. Remove this, it is too much. Okay. So tan theta is equal to f of xn, and if we see this tan theta, which is delta y by delta x, and x, the step size is h. Let's say we are using h as a step size, and delta y, let's say we want. So let's say this value is yn. So yn plus 1 is nothing but yn plus delta yn, and if we use this previous expression, we'll get yn plus delta y will be h into f of xn. So this is the Euler method, where we are so here we are just getting the derivative and multiplying with h. That will give the increment in y value, and we'll get the approximation for yn plus 1. Okay, so this is the question. So 3 dy by dx, 3 dy by dx plus 5y square is equal to sin x. 3 dy by dx plus 5y square equal to sin x, and y of x, y at x of x equal to 0.3 is 5. So y is equal to 5. Okay, and the step size is given to be 0.3, and what we want to find out is value of y at x equal to 0.9. 3 and y at 0.9 is 2. We have to find out. So if we, so there are a few steps only we have to take. So let's say this is x0, which is 0.3. If we add the step size, it will be x1 is equal to 0.6, and next step size x2 is equal to 0.9, and this is the number of steps. So number of steps we can find out by xn minus x0 by the step size. So xn is 0.9, x0 is 0.3, and the step size is 0.3. So it will be 0.6 by 0.3 equal to 2. So 2 steps we have to take. So first we'll go from here to here, and then from here to here. Okay. And one more thing we'll do is we'll simplify this dy by dx. So dy by dx is equal to sin x minus 5y square by 3. Okay, so this is nothing but function x, function of xy we have. Okay, so y at x naught, that is y at 0.3 is equal to 5, and x naught is nothing but 0.3 here. So if we find out f of x0 y0, so f of x0 y0 will be sine of x0 is 0.3 minus 5y square minus 5 y0 is this is y0, which is 5, and divided by 3. Okay, so okay, so we'll compute this sine of 0.3 minus 5 into 5 square, 5 3. Okay, so this is minus 41.5682. Okay, and y1 is equal to y0 plus h into f of x0 y0. So y0 is 5, h is 0.3, that is already given. So 0.3 into minus 415682. Okay, so y plus 0.3 into answer, that is minus 7.4704. Okay, so this is y1, and x1 is x0 plus h, which is 0.3 plus 0.3 is 0.6. So we will use this values of x1 and y1 in the next step, and y1 is minus 7.4704. Okay, so f at x1 y1 is sine of x, so x minus 5y square, say minus 5y square by 3. Okay, that is sine of 0.6 minus 5 into y1 square minus 7.4704 square by 3. So if we do this calculation, sine of 0.6 minus 5 into this is the previous value of y raised to 2. Okay. So this is minus 92.8232. Okay, and y2 is y1 plus h into f of x1 y1, and y1 is minus 7.4704, h is 0.3, and f of x1 y1 is this one, it is minus 92.8232. If we do this calculation, plus 0.3 into minus 92.8232. So this is the answer, value of y2 minus 30.31. Okay, so y2 is nothing but y at 0.9, and that we have found out, because x2 is x1 plus h, which is 0.6 plus 0.3, which is 0.9. Okay, so we have found out the y2, which is minus 30.5.31. So this is the correct answer. Okay, so this was the Euler method, and this method is a straightforward method. Okay, so we'll go to the next question. The second order Runge-Kutta method uses as a predictor. So one second. Okay, so first I will write what is the like how this Runge-Kutta second order method works. So in this case, yn plus 1 is equal to yn plus half, and k1 plus k2, and k1 is h times f of xn yn, and k2 is h of f of xn plus h, comma yn plus h into h is already multiplied to, so plus k1. So you can see this term where what we are computing is yn plus k1, so that is yn plus k1 is h f of xn yn. So in this case, as already we have seen, this is nothing but the Euler method. So in the Euler method, that's what we have used to predict the value of the function at next location. So this is the, so here that what we are computing is nothing but the prediction for the yn plus 1. So this k2 we can write as f of xn plus 1 comma y of n plus 1. Okay, and this is nothing but the forward Euler method that we used in this case, and here we are like getting the prediction. So and so you can see that whatever value we have got, we have, but that is not the value we are finally computing. So this we can treat as the predicted value, and then after prediction we are again finding out the yn plus 1, and that time we are using this two values that we have computed. So first value, in this case we have find out the derivative at x and yn, and in the next case we have find out the derivative at next location, which is that which is at xn and yn plus 1. But this yn plus 1 we have just predicted, but we have not yet corrected this value. So in this next step we have what we are doing is we are using this average derivative value. If we just remove this h, this k1 and k2, they corresponds to the average the slopes at first location, or if we have this two locations. So in this case we are approximating slope at this location, like computing the slope by this function, and next location we are computing the slope by this, and we are anyway this location, which is let's say location 2 and location 1. So this second location is approximated, we'll say n and n plus 1. So n plus 1 location we don't have the exact value of yn, so here we are using the approximate value. So this is the approximate value. So this approximate value we are using to compute the derivative at n plus 1 location, and then this slope at n location and slope at next location we are taking the average, and then that average we are using to compute this step size, and then we are finding out the next instant value yn plus 1. So this is nothing but the corrector step. So in this case we are correcting, and this step you can see this is whatever we are doing, this is the predicted value. So this predicted value is forward Euler. Okay, I hope this is clear. So this is why this is forward Euler method for Runge-Kutta second order method.
Can we have a problem solved on this one?
Hello.
So having a problem solved on this by taking some examples of nature.
You're saying is there any example problem on RK method, is it?
Yes, sir.
Okay. So first I will complete this whatever questions I have, and then I will come back here, or let's say we'll just create one problem randomly. So let's say dy by dx is equal to let's say x, and at x0 is let's say 1, and y0 is let's say also 1. So what we want to find out is let's say what we are interested in, what is y1. So what we can do is and let's assume that we are taking the step size equal to 1. So we'll in first iteration itself we'll get the value, and let's say we'll integrate this first directly and see what is the value, and then we'll compute by RK method and we'll see what is the value. So if we integrate this, so it will be y is equal to x square by 2 plus some constant, and if we substitute these values, so it will be 1 is equal to half plus c, so c is equal to half, so y is equal to x square by 2 plus half. So if we compute the x0 y0, which will be x will be 1, so that is 1, so that is correct. And if we substitute as x is equal to let's say we are interested now in x1 is equal to, let's say, 2. So x is equal to 2, we'll get y is equal to 2 square by 2 plus half. That will be 2 plus half, this is 2.5. Okay, so this is what we are expecting as answer, y is equal to 2.5. Okay, so now we'll solve the same problem with RK method. So dy by dx is equal to x, or we can say this is our f of xy. So in this case, x0 is equal to 1 and y0 is also 1, and let's say we are using RK2 method. So in this method, yn plus 1 is equal to yn plus half k1 plus k2. Okay, so here we want to find out y1 is equal to y0. So here n is equal to 0 for us. So in this case, y1 is equal to y0 plus half k1 plus k2, and k1 is equal to h into f of x0 y0. So h is 1, so that is fine, and f of xy is it will be x0 itself, and x0 is 1, so it is 1 into 1, which is 1. Okay, so this is k1. k2 is equal to h into f of x0 plus h comma y0 plus k1. So h is 1, we are taking the one step, and f of x plus h, whatever x we are taking the value, so it will be x0 plus h, and in this case x0 is 1, h0 is 1, so it will be 1 plus 1, which is 2. Now if we compute the value of y1, so y0 is 1, then half k1 and k2 is 1 plus 2, which is 1 plus half of 3, which is 1 plus 1.5, which is 2.5. Okay, so in this case this answer is matching whatever we have started with. You got it?
Yes, sir. No, I understand.
Okay, so this is so in this case, Runge-Kutta method, we what we have is the gradient of the function or derivative of the function, and so initial value will be given. So in this case, we will have the initial value, and then this at each location we can find out the slope, and based on this slope we want to find out, let's say, at next time instant what is the value. So if we just use the slope at this location to compute the next value, that is Euler method. But in this Runge-Kutta, we are not just taking the derivative at this location, but we are predicting the value at this. Just zoom in. So that's it. So let's say if we take the find out just based on the slope, the Euler method. So for Euler method, if we use the slope at this location, this value will be the predicted value, but actual function value is here. So the slope, so this predicted value we have to bring it down. So instead of just using this f at this location, so this f at this n predicted, let's say, location is also used. So these two slopes if we used, then this value can be, let's say, not exactly, but can be brought down closer to this value. So that is the main idea in this Runge-Kutta method. So k1 is the slope at k1 is based on this slope at this location, and then k2 is based on the slope at this location. So this, if we take the average slope of this two values, which is fn and fn predicted, that will give the better approximation. So in that case, if so, this is the average, or you can say this is the average slope. So this average slope if we use, it will be yn plus 1 is equal to yn plus h into slope average, and this slope average is nothing but this one. So that's how this method is like getting better approximation. Okay, so we'll go to the next method. Next question: the Newton-Raphson method fails when? So we'll see first what is the Newton-Raphson method. So in Newton-Raphson method is, so what is Newton-Raphson method is used for root finding. So let's say there is this function y is equal to f of x, and this is, let's say, this is iterative method. So let's say at xn, this is the function value fn, and the slope at this location, or let's say we draw the tangent at this location, so that will intersect at this location, and we can see that this is the root we are interested in, and this value is moving closer and closer towards this root. So if we next instant, if we find out the slope at this location and take the tangent, that will again move closer to the root, and again if we go on iterating, it will finally go towards the root. So this is the, let's say, theta angle. So tan theta is equal to so that is the derivative of this function at xn, or we'll say f dash n. And if you see this triangle, let's say this ABC triangle. So in ABC triangle, this tan theta is nothing but BC by AB, and BC, so let's say this is our, after n plus 1 iteration, we reach this value. So that is xn plus 1 minus xn, and BC is nothing but the function value at n location. So the equation that we have is f dash of n is equal to f of n by xn plus 1 minus xn, and we can write xn plus 1 minus xn is equal to fn upon f dash n. So xn plus 1 is nothing but xn is that correct? In this case it should be opposite. Yeah, so we are finding this distance, so xn is larger, so xn minus xn plus 1, xn minus xn plus 1, xn minus xn plus 1, and xn plus 1 is equal to xn minus fn upon f dash n. Okay, so this is obvious that if this value should not be equal to 0, so if it is 0, it will be it will give the next xn value, which is infinity. So that situation occurs when, in case, let's say, if we are having the sine wave, which is In this case, if we start with this location, so we are expecting that we should go to this route, but based on this tangent, if we draw, it will just go to infinity or any direction. So in that case, we it will not give the closest route, but it will just go to infinity. So this will fail if the derivative is 0. So this is the correct answer. Okay, so we'll go to the next question. The trapezoidal rule can be used to evaluate. So the answer is, in your integration we will be computing using the trapezoidal rule. So we'll see what is, in brief, what is trapezoidal rule. Uh, so so trapezoidal rule is used to compute integration. Let's say f of x dx, and it can be y as a function of x dx. Okay, so this integration can be computed with trapezoidal rule. In trapezoidal rule, what we'll do is we'll divide this interval, let's say, equally, and this is x equal to a and x equal to b, and the numbering, let's say this is x0 and this is xn, and in each interval, so the curve shape, okay, so in this case, we just know these values at discrete x locations, let's say. So in that case, we can approximate this curve by linear interpolation or by linear curve, and you can see that this is the trapezoid. In this trapezoid, this is the can be treated as height, and this is these are the parallel sides. The length of this is y1 and y2. So if we say this is area 1, so area 1 is nothing but half into height, which is h, and the sum of parallel sides, which is y0 plus y1. So that is h by 2 y0 plus y1. And if you want to compute this whole area, so in that case, the integral can be approximated by summation of this area, and let's say this is nth area, so I is equal to 1 to n. So this is the composite rule, where we will add all this area. So adding all this area is the whatever equation we will get after this will be the composite rule. So in that case, you can see that this sides will be considered twice, but the starting side, which is the y0, and this is yn, so this and this will be considered only once in this case. So the composite rule will be y0 plus 2 times, so this is y1 y2 till yn minus 1, and finally yn. So this is the trapezoidal rule. Okay, and it has been used to approximately compute the integration. Okay, so we'll go to the next question. One dimensional heat equation is this one, is dash dash in nature. So I will write for general case how to find out the classify this equation. So let's say we have the partial differential equation dou square a u by dou x square plus b dou square u by dou x dou y plus c dou square u by dou y square plus c d dou u by dou x plus e dou u by dou y plus f is equal to 0. So this equation can be classified into 3 classes based on, so the reason is not given, but there are this equation can be solved with characteristic equations, and there will get one characteristic, uh, two characteristics, so for these equations, so whether we get the characteristics or not, that will be decided based on the discriminant, and based on that discriminant they are categorized. So in case of let's say parabolic parabolic if this equation will be considered as parabolic if b square minus 4ac is equal to 0, and it will be considered as hyperbolic if the b square minus 4ac is greater than 0. So in this hyperbolic case, there will be two characteristics, and if you know the wave equation, so the wave can travel in for 1D case it will be travel into, let's say, plus c and minus c, not don't this is not that c, so let's say this is c1 and this is c2, let's say this is c1 only. So this is the wave speed in which the wave will be traveling. So the wave equation is hyperbolic, and parabolic, hyperbolic, and elliptic. And elliptic case, b square minus 4ac will be less than 0. So in this case there will be no direction in which the wave will be propagating, and that's why you can say that it is equivalent to say that it is propagating in all directions. So that is elliptic case, or any solution at any point will be influenced by all the points which are surrounding to it. So that is elliptic case. Okay, so if we come to this equation, so we can write this equation, that is dou u by dou t is equal to alpha square dou square u by dou x square. So alpha square dou square u by dou x square minus dou u by dou t equal to 0. So this is the standard form, and in this case a is equal to alpha square, b is equal to 0, c equal to 0, and in this case when we are classifying this equation, we are not considering these terms which are linear terms, or not. This equation itself is linear, but this first order partial differential terms we are not considering. So if we compute this a square minus 4 b square minus 4ac, b square is 0, it will be 0. Okay, so in this case it is 0, so it is parabolic. So this equation is parabolic. This is correct answer. Okay, so this is the, I hope you understood this. Okay, so next question is we have to evaluate the integral. The value of this integral using Simpson's 1/3 rule will be. Okay, so first of all, last time I derived this equation for Simpson's 1/3 rule. So this is also used for computing the integral, let's say from a to b y of x dx. And let's say if we just consider the one interval for this, so let's say this is x0, x1, x2, and then their corresponding values are y0, y1, and y2. So in this case the integral will be approximated as h by 3, then y0 plus 4y1 plus y2. Okay, so this is the first part. And then if we have multiple like if we have the bigger like if we consider the multiple sub intervals, So let's say this is, we are considering, let's say 6 intervals. So this is x0, x1, x2, x3, x4. Okay, and so what we will get here is h by 3. So first of all we will compute for this a region which will be, this is y0, y1, y2, y3, y4. So it will be 4 y1 and y2 plus h by 3. Then we'll compute the area for this, which will be y2 plus 4y3 plus y4. So if we calculate, simplify this, we will get y0 plus these two terms are there which have the 4 as coefficient, which is y1 plus y3, and this term is come twice, so twice y2 plus y4. So the terms in this bracket are odd and term in this bracket is even, and this is the last value, this is the last value of the function and this is the first value. So in general what we can write this as h by 3 y0 and let's say 4 into odd terms and 2 into even terms and yn. So this is the Simpson's 1/3 rule, and we'll solve the question now. So the integral 1 to 7 dx by x. So integral 1 to 7 dx by x. So there are so interval, the step size is not given. So what we will do is we'll assume that step size to be 1. In that case we'll just see whether we can use the Simpson rule with the step size of h equal to 1. So in this case I'll just graphically draw and then we'll see. Okay, so at a time we will be considering the 3 points. So these 3 points will form the first interval, then next these 3 points will form the next interval, and after that this 3 points will form the next interval. So we can use the step size as h equal to 1, and in this case this will be x0 and this function height, let's say, will be y0, and this will be x of, this will be x1, this is x2, x3, x4, x5, x6, and this will be y6. Okay, so I will create the table. So x, y, so x is equal to 1, 2, 3, 4, 5, 6, 7. So the function that we are integrating here, so here the y is equal to 1 upon x. So in this case it will be y equal to 1 upon x. Then in next interval, or next, for x equal to 2 it will be half, then it will be 1 by 3, 1 by 4, 1 by 5, 1 by 6, 1 by 7, and this will be y0, y1, y2, y3, y4, y5 and y6. Okay, so now we will use this equation for Simpson 1/3 rule to compute the integral. So in I is equal to h, we are taking 1, so h by 3 will be 1 by 3. Then we are supposed to take y0, so y0 is 1, then 4 into let's say odd terms. So these are the odd terms, y1, y3 and y5. So y1 is half, y3 is 1 by 4, and next is 1 by 6. Okay, then we are supposed to take 2 into even terms. 2 into even terms. So even terms are y2 and y4. y2 is 1 by 3, y4 is 1 by 5. Okay, and y6 is 1 by 7. Okay, so this integral is equal to, we'll get the value if we calculate. I will just write it. It is 1 by 3 1 plus 4 into half 1 by 2 1 by 4 plus 1 by 6 plus 2 into 1 by 3 plus 1 by 5 plus 1 by 7. Okay, so we have taken this first term, then we have taken 4 into odd terms, 2 into even terms, and last term. So 1.9587. Okay, so this is the answer. So 1.95, this is the correct answer. Okay, yeah, then we'll see the next question. The partial differential equation is called as, okay, so this is the Laplace equation, but we'll write the all equations once just to revise. So this is the Laplace equation. For heat equation, it will be dou u by dou t is equal to alpha square dou square u by dou x square. Then wave equation is dou square u by dou, it's a t square, dou t square is equal to c square dou square u by dou x square, and you can see the dimensions. And for Poisson equations, dou square u by dou x square plus dou square u by dou y square is equal to some function of xy. So here if it is 0, that will be Laplace equation. If it is non-zero, then it will be Poisson equation. Okay, so we will go to the next question. So consider the following partial differential equation for u of xy with the constant c, and this is the equation given, dou u by dou y plus c dou u by dou x. The solution of this equation is, okay, so this actually represents the wave which is moving in particular one direction. So we'll find out what direction it is moving. So we'll start solving this. So dou u by dou y plus c dou u by dou x. Okay, so the one thing I will do is, instead of y I will use t. That is much like we can understand it more better if we consider this y as the time, and this is c dou u by dou x equal to c. Okay, and so let's say this is the x-axis, and this is actually represent the wave, where let's say we have some waveform initially. I will just draw a simple hat function. So in that case, if c is positive, this will be moving in this direction. So this is, let's say, at t equal to 0. So there will not be any change in the shape, but it will just move forward in this direction. and this is x, and let's say this is at some next time instant t equal to t, let's say. So at time t, this is the shape, this is the location. The shape of the function is unchanged, but it has moved to this side, and this location, the direction in which it has moved, it will be the distance it has covered will be ct. And if we, so you can see that this is nothing but the just shifting the origin, shift of origin. So we can directly write the solution here itself. It will be y equal to, so whatever function it has, so it will be f of x minus ct, and t is nothing but y, so it will be x minus cy. So this is directly we have written, so this is the correct solution, but we'll see how to get to that solution with this. Okay, so this is the differential equation, and let's say this is the initial state. So u at x and t, let's say at t equal to 0, at t equal to 0 we know the form, so this is, let's say, f of x. So at f of x, this is the, so this is nothing but the u equal to, or we'll say this is u naught, or we'll just say f of x, that it will be better. So at t equal to 0, whatever the form this u have is nothing but f of x. Okay, so how to solve this equation? So what we will do is, so this c is there, so c, so in order to convert this into the total derivative, if we use c is equal to dx by dt, so you can see that what we will get is du by dt plus dou u by dou x and dx by dt. So this is nothing but the total derivative of u with respect to time, and that is nothing but the 0, because this is already given to be 0. So we can say that dou u by dou t is 0 if c is equal to dx by dt. I will write it. So du by dt is equal to 0 if dx by dt is equal to c. So so what it means is, if we are moving with this velocity or whatever coordinate we are considering, so initially let's say we are at this location, and at time t equal to 0, if we are at this location, we'll see the same height of the function. So we will feel that there is no change in the value of the function if we are moving along the x-axis with speed which is c. So that's what it means. So this is the known as method of characteristics, and in this case we can see that u is equal to constant, and we'll write it more detail. X of t is constant. So x of t is constant means u at, let's say, this x is there, so we'll say x of some at previous instant, so this x we are moving, so in this case x is the our location, let's say we are moving with this speed, so x is our location at time t equal to t, let's say this time t, and time t equal to 0 we were at some location which is xp. So I hope this is clear, so whatever I am saying. So u of xt is constant, but that is the time derivative is constant, so it must be fixed. So whatever the state of this u will have at time t equal to 0 must be the value of the function. Okay, so we will just now integrate this dx by dt equal to c. So in that case we'll get x minus, let's say xp is our initial state at time t equal to 0, so it will be ct, and here we can see that xp is nothing but x minus ct. So we can write u is equal to, and so whatever the if you see here, we have assumed that at initially the value of this uh, or the shape of this wave is f of x. So if we can write here as f of xp, okay. And then this xp value, so instead of xp we'll write x minus at. So u of x t is equal to f of xp, and xp is nothing but f of x minus cd. Okay, so this is the like if we start with the differential equation, this is the way to get to the solution. So in this case what we are doing here is we have this one second. Okay, so we have this equation. So in this case what we are doing is we are assuming this c to be dx by dt, and once we assume that it is dx by dt, then it will convert into total derivative. So if u is a function of xy, so the, or let's say we are interested in t, so du by dt is nothing but dou u by dou t plus dou u by dou x dx by dt. So in this case this c acts as a dx by dt, so that's what we have used here. And what we are now saying is if c is equal to dx by dt, the total derivative of u with respect to time it will be 0. So what it means is if we du by dt is 0 if dx by dt is equal to 0. So in this case if we are moving or whatever location we are interested is in, if our location changes at this speed, we will feel that u is a constant. Okay, so in this case u we have anyway is a constant we have said. So u of x of t, we are moving, so in this case let's say this is constant, so whatever the shape of this u will have at time instance equal to t equal to 0 should be conserved, so this shape will not change. So that constant we have equated to u of xp at 0. And now this xp, so whatever the initial condition, we have already specified that initial shape of the wave or shape of the function is f of xp, so that we have written here. And this xp, you can say that current location is x at time t. So what would be the location at time t equal to 0? So that we are finding out. So this is the location at t equal to 0. So you can see that if you put this t equal to 0, so that is nothing but the location at t equal to 0. So if we so xp, so if we write x and t, so this is at t equal to 0, this is the location, and now we have moved to this at t equal to t. So what we are interested is in, so this is the current location. So if our current location is x at time t, what would be the location at time t equal to 0, that is xp, and that we computed using this relation, because we know that at what speed we are moving. So this is nothing but initial location we have found out. And if we substitute this xp in this equation, we'll get x minus ct. So this is nothing but if you simply come back to this whatever waveform I have drawn here, so in this case if we see this wave is going towards right, so you can see that this wave has moved forward. In this case the origin has shifted to x is equal to ct. So if we have the function f of x, and if you want to shift the origin, so that time we have to shift it this way. So x, so if we say x minus ct is equal to 0, so x is equal to ct. So this is kind of our origin for this function we have shifted. So that's how this equation we can solve. So in that case we will see that this dx by dt equal to 0, and this is nothing but the characteristics. So dx by dt is known as characteristics dx by dt is equal to c, and along, so dx by dt, if we draw in xt plane, so it will be dx by dt. So let's say this is the x and this is time. So dx by dt will be the slope, and this will be having c will be the like this, and along this line the function values will be constant. So along these lines function value will be constant. So that is the meaning of this characteristics line, where the function value will be constant. Okay, so I hope this is clear. Okay. So Chandan, was that clear?
Sir, a bit confusing, sir. Like, I got not so clear, sir, but understood the concept a little bit.
Okay. Yeah. Okay. So you can go through once and try to derive yourself. I think it will be clear. Okay. So I will take one problem on householder method. So this is I will just give some explanation of this, mostly in this, what is householder transform, what is householder matrix, and yeah. So let's say this is a vector. So let's say this is a u vector, and there is some plane. Let's say if I draw in 3D, so in this case this plane will be defined by the normal vector w. Okay, so let's say instead of this dealing with this 2D 3D, what we'll do is we'll deal everything in 2D, because anyway in vectors things will not change even if we do in 2D or 3D. So what I will do is let's say this is u vector, and let's say we want to reflect this vector along this line, or in case of 3D it will be plane. So let's say this is the normal vector w, and we want to reflect it along this, so it will be like this. So let's say this is u reflected vector. So how we can do this reflection? So we can see that let's say this w is unit vector, w is unit, okay, it's unit vector. So in what it means is let's say the vector in general will be written as like this, w1 w2. So w transpose w, if we take, so it will be w1 to, let's say, wn, it will be w1 to wn. So if we do this multiplication, what we will get is square root of w1 square plus w2 square, and so on. So that will be 1, so because it is unit vector. So this is the w, and if we want to, let's say, project this u on w, so this is the projection, and you can see that if we go in this direction twice as that of this projection, we will reach to this ur. So okay, so first of all we will find out this projection. So this we'll say this is a p vector, and I will so So let's say this is the plane, this is W, this is U, so as much there we should come here also, and this is U reflected. And if we take this projection, so this projection, let's say this will be in this direction, and this is, let's say, P vector. So if we see this P, so P, what will be the length of P? It will be U, let's say W transpose U. So W transpose what it, so this is nothing but the dot product. So this is W transpose U, and then we are supposed to divide by magnitude of W, which is already 1, and this, so this is nothing but the magnitude, and this is the projection, so magnitude of the projection, and the direction will be W. Okay, so I hope you got this. So this is the first term is the magnitude of projection, and then this W, if you multiply, this will be the direction or unit vector in that direction. So P will have the magnitude of P, and it will have the direction. So the direction will be W, and this magnitude is the projection. And you can see that if we add this minus P twice, we will get UR. So UR is equal to U plus, actually it will be minus 2 times P, and this P is 2 times P is nothing but W transpose, and write W transpose U W. W transpose U times W, and this is W transpose U is nothing but the value. So you can see that W transpose W has just given the magnitude. So similarly W transpose U is dot product, so that is also single value, so it doesn't matter in which order we are doing this operation. So we can, so that is nothing but the scalar. So UR is this one. So we will simplify this, and you can see what we will get. So UR is nothing but U, and then twice we have to subtract this projection. So this W and W transpose I will take together, and this U I will keep outside. Okay, so in this case if we write this, we will get I minus 2 W transpose U, and this is the UR. So so this is how we will get the reflection of U, where the about the plane with the normal equal to W. Okay, so UR is a reflection of U about a plane with normal W. So this normal vector W, there is a plane. So you can see that this matrix is like a matrix transformation is transforming this U from U to UR. So this matrix is, let's say, capital U, which is I minus 2 W transpose, and this is known as householder matrix. Okay, so this is the householder matrix, and one more thing I will explain is, let's say a rotation matrix if you know rotation matrix. So let's say this is the vector. It has let's say the coordinate which is r cos theta and y will be r sin theta, where r is this length and theta is this angle, and we can write as xy also. So what we want is, let's say we want this vector to rotate by some angle. Let's say this angle is alpha. So in this rotation, what we are interested is in this r magnitude should not change, and let's say this is x1 and y1. So what we want is x1 and y1. Somehow we want to get this from the xy. So you can see that for x1 and y1, this coordinate is r cos of the angle will be theta plus alpha, and r sin theta plus alpha. So if we expand this, this first term will be, so we'll write it separately. Let's say x1 is equal to r cos theta cos alpha minus r sin theta sin alpha, and r cos is nothing but x, so x cos alpha minus r sin theta is nothing but y, so that will be y sin alpha. So we can, so this cos alpha we can write here cos alpha and minus sin alpha. Okay, and then similarly we can write y1 will be r sin theta cos alpha plus r cos theta sin alpha. R sin will be y, so I will write it here y cos alpha plus r cos will be x, so x sin alpha. So it will be sin alpha cos alpha. So this is the rotation matrix. So you can see, we'll see in like take the transpose and we'll see what happens. So this rotation matrix is cos minus sin, cos, let's say cos alpha minus sin alpha, sin alpha cos alpha. Okay, so this rotation matrix, if you see the columns of this, so we can, like, instead of doing individually, what we can do is, let's say we will try the let's say this, we'll take the transpose of first column, say cos alpha sin alpha and cos alpha sin alpha. So this is the first column we are taking. So let's say this is column 1 and this is column 2. So this is nothing but column 1 transpose column 1. So if you see this, it will be cos square alpha plus sin square alpha, which will be 1. And similarly, if we take the C2 transpose C2, that will be, so you can see that this first column, magnitude of first column is 1. So similarly, if we take the magnitude of first column, second column, which also will be sin square alpha plus cos square alpha, that also is 1. So we can see that these are the C1 and C2, they are unit vectors. What happens if we take the dot product of C1 and C2? So if we take the dot product of C1 and C2, it will be minus, so this is the first column component, this is second component, it will be minus cos alpha sin alpha plus sin alpha cos alpha, that will be 0. So you can see that this columns, each column have unit magnitude and their dot product is 0, so means they are normal. So that also we can see by, let's say, r. So we already saw that, but if we write r transpose r, so in that case it will be cos minus sin alpha alpha, and then it will be sin alpha cos alpha, and then cos alpha minus sin alpha, sin alpha cos alpha. Okay, so in this case what we will get is, so this if we multiply, it will be cos square plus sin square, which will be 1, and next if we multiply to this, it will be cos minus cos sin plus cos sin, which will be 0. Similarly it will be 0 and this is 0. So in this case you can see that this is like the columns are having the magnitude which is 1 and they are also normal. So R is ortho normal matrix. And what we want, so what I want to say is, if this matrix is ortho normal, so in this case this magnitude of this vector, you can see that this initial magnitude of vector was r, and after multiplication also it was r. So if we have, let's say, r times, let's say, some vector b, and if we got some vector, let's say c, so magnitude of b is equal to magnitude of c. So in this case, in case of ortho normal matrix, the magnitude will be magnitude will not change, only the direction of the vector will change. Okay, so we saw what is householder matrix, is this one. And one more point I want to make was, if we have orthonormal matrix, the magnitude will be the same. Okay, so let's say we have some vector b, and let's say this vector b has terms, let's say. So I will let's say this is b1 to bn. So what we want, let's say, is b1, b2 and br, and after this br, let's say, we want all terms to be 0. So this transformation we want, let's say. So in order to get this transformation, so we saw this transformation. So in this transformation, what matrix we should use to get this transformation? Okay, one more thing. Okay, this might not be b, but till this point it will be br minus 1, and let's say this is alpha. So so we want till this nothing is changed. So this is 1 to r minus 1, nothing has changed. After that one term is there, and all terms which are below, they are 0. So this transformation is achieved using householder transformation. Okay, I hope this is clear. So we have some vector b, and what householder transformation will try to do is it will try to find out the matrix u. So if we multiply this u into b, so finally that matrix that we will get will have this form: b1 br minus 1. After this it will be some term alpha, and all lower terms will be 0. Okay, so this is the householder transformation. So this is the householder matrix that performs the householder transformation. So we'll see If we want to find out this u, how to go about that? Okay, so this might be like, might take some time, but just stick with this and then we'll solve, like find out how to find the u. So anyway, we know the form of u, but the form of u is known, but the terms we don't know. So how to find the terms in that? So u is nothing but the householder matrix. It has the form I minus 2 w times w transpose. Okay, so this is the matrix, and if you see, let's say we have this vector b, and this b, let's say we divide into b and let's say d. So this c is nothing but the top part, which we have denoted by b1 b2 till br minus 1. So if you see this is, I'm referring as c, and this part is d. So d is nothing but alpha 0, and this c, the size is r minus 1, and it has m, where m is equal to, so this total vector is of size n, so n, and we are not taking this r minus 1 terms from this, so it will be minus r plus 1. So this is the shape of size of d. Okay. So so you can see this c part is unchanged. So if you know that if we have some identity matrix, and if we multiply by c, it will be c again. So you can so if we are performing this transformation u into b, where we want this c part to be as it is, and below this part we want alpha 0. So what we want is I here this should be 0, and this part will have let's say some terms. I will say let's say this matrix itself is u1. I will just mention here is u. So this is u times c d, that will give c here, and this part will be u times d. Okay, so what, okay, I hope I am not confused you. So this u is the householder matrix, and b is the vector that we want to transform, such that if we okay, actually I should have used a different notation for this. Okay, so this b1 was initially having all this b1 to bn terms, and after multiplying with to this by u matrix ub, it is giving this alpha, and then below terms are 0. So okay, so I think this b has created some problem. Okay, so this is b matrix, so I will use some different name. So let's say this is a matrix. Sorry, I think I make problem. C D. Okay, let's keep this everything like this. Okay. Okay, we'll use b only. So b, if we apply, so in this case I will change this part, Okay, so D is nothing but B R2 B N. Okay, so this is D. So if we apply this, so UD we want to be, so UD that we want to be alpha 0 0 0. Okay, I hope now it is clear. So so B is some vector which has term b1 to bn, and what we want to do is we want to transform this B into this form where this first r minus terms are as it is, then there is a rth term which will be which can be anything, but then after this these terms are 0. So this term this is how we want to transform it. Okay, so to do this transformation we are using this householder matrix U, and the terms in this U matrix we want to find out. So if we multiply this UB into B, so we will get these terms will be as it is, this has been alpha some value, and this terms is the lower term below that is 0. Okay, and this is not CD, because we have now redefined the CD as this one. So B matrix we are using C and like we are representing in two parts, C and D. So C part will be B1 to BR minus 1, so this will be unchanged, and this part will be changed. So to keep the part unchanged, so what we want is this U matrix for the part that multiplies with C we have made as identity, so that C after multiplication we'll get C as it is, and then the next block, so this block we have kept 0 and this block also 0. So this block which is U we are will get multiplied to this D, and that will give the desired value where UD will be alpha and the below terms will be 0. So this will be the case. So in overall what we are getting is, so this we mentioned this U1, so U1 times B will get C, and this D is the lower part of this which will be alpha 0 0. Okay, and this U1 we are considering as identity 0 0 U. Okay, now we will see how to find the terms that are involved in the U. Okay, so already we mentioned that we will be using householder method matrix. So U will be I minus 2 let's say V, and so what I'm changing the from W to W transpose, that I will explain in a minute. V into V transpose. So why I'm using this, because this U1 matrix we are treating as identity minus 2W W transpose, and W what we will do is we'll say 0 0 and last lower term will be W. So this will be first R minus 1, and this will be N minus R plus 1 terms. Okay, so why it is done is because if you see this W W transpose, if we take the W W transpose, so we'll get 0 here, because this first term are 0, this is also 0, this is also 0, and we'll get V transpose V transpose. V transpose, and if we add the identity matrix to this, so this will be identity matrix. It will be R minus 1 cross R minus 1 identity part, and here also it will be I minus, but this will be M cross M, where M is nothing but N minus R plus 1. Okay, I think you can, like, it might be confusing now, but you can check it once by yourself. Okay, so finally what we will get here is identity matrix. Okay, I will write on the next page. So this is u1. So u1 is equal to identity plus w transpose, and this identity matrix we can write as identity matrix which is r cross r. This identity part will be m cross m 0 0 plus w that we are considering, it will have 0 0 0. Then this is v which will be of m size. This will have 0 zeros, then it will be vm transpose. If we do this calculation, it will be I r cross r, it will be 0 0, it will be I m cross m minus vm transpose. Okay, and this matrix we are treating as u. Okay, so and you can see that if we now multiply this u1 times b, which will be, let's say, I will not write the sizes now, I minus u times cd, it will be c u d. Okay, so so in this case you can see that c has not changed, but we are multiplying here ud, and this u into d we want to be alpha 0 0 0. Okay. So this is the aim. So first we have to find out the u that will do this task, and we have defined u is equal to I minus 2v transpose, and magnitude of v is equal to 1. Okay, so if we take u transpose u, what we will get is I. So I will write directly the transpose. So here it will be get transpose, it will be again v transpose, and it will, so basically it is a symmetric matrix. So if you do this multiplication, it will be minus 2v transpose minus 2v transpose minus minus plus 4 v transpose v transpose, and v transpose v, we have already said that v is unit, like the length of v is unity. So v transpose v is nothing but magnitude of v, which is 1. So this term will be 1. So u transpose u will be I minus 2, so 4 v transpose. Okay, so it is actually changed from u to v. Okay, so everything is v here, nothing is, no u on right side. So v transpose plus 4 v transpose. So this term will get cancelled, and I. Okay, so you can see that u is orthonormal. Okay, so if you remember, I just showed that for rotation matrix, which was orthonormal matrix, so in that case the length was not changed. So that's why I like discussed this rotation matrix here. So okay, so you can see that if u is a orthonormal matrix, so even if you multiply, like if you do this transformation, the magnitude should not have changed. So magnitude of d should be alpha. Okay, we'll see it here. So u is orthonormal, So UB is equal to alpha 0 0 0. So in this case, magnitude of, okay, so we are now at this location UD. So I will write D only. So UD is equal to alpha. So magnitude of D is equal to alpha. Okay, and this is also 0. Okay, so that's how we can find out what should be the value of alpha. Okay, next point is this U is equal to I minus V transpose and 2. Okay, so if we write in this, so we'll get I minus 2V transpose times D is equal to alpha. I will write in this way, transpose, let's say. And if we multiply, let's say, both side by, let's say, V transpose, so what we will get is V transpose D minus 2 V transpose V transpose D is equal to let's say V1 V2 times alpha 0 0. Okay, so why I multiplied with V transpose D is, so this term will get cancelled because V transpose V is 1. Okay, so what we have is V transpose D minus 2, this is equal to 1, so minus 2 V transpose D. Now you can see that this 2 term has become same, is equal to V1 alpha. Okay, so it is minus 2 V transpose D is equal to V1 alpha, and what we'll say is, let's say V transpose D is equal to P. Okay, so you can see here that, I hope you have got this. So if you do this multiplication, all terms will get cancelled, only V1 alpha will remain. So this is scalar only, yeah. So this is scalar, and this is nothing but some, so we will say this value has some P value, V transpose D. So minus 2P is equal to V1 alpha, and okay, so okay, though this after subtraction will be getting this not 2, which will be V1 alpha so this is P is equal to minus V1 alpha. Okay, so what we will do now is we'll substitute this into this expression, into D. So we have this expression here, so we'll substitute into this expression I minus 2V transpose into D is equal to this alpha 0 0 0. Okay, so D minus 2V, V transpose D is nothing but P, so V transpose D is nothing but P, and P is nothing but V1 alpha. So I will write V1 alpha here, and that is nothing but alpha 0 0 0. Okay, So even though this derivation is long, but you will understand why we are doing the calculations and the way we are doing. Okay, so d minus 2v into v1 alpha is equal to alpha 0 0 0. Okay, so now we will write d1 d2 d3 till dm minus 2 vm v1 v2 vm into v1 alpha is equal to alpha 0 0 0. Okay, so if you write the first equation, d1 minus 2 v1 square alpha is equal to alpha, so we will get v1 is equal to v1 square, let's say d1 minus alpha by 2 alpha. So if we one second, is that correct? Okay, so here I substituted the p value, which should be minus, actually minus v1 alpha. So minus v1 alpha is there, I missed the sign here, so it will be d plus actually. Okay, so this should be plus. Okay, so v1 square is equal to alpha minus d1 divided by 2 alpha. So we can take alpha out, half out, and then 1 minus d1 alpha. And one more thing is this alpha is there. So if we so let's say this alpha is in our control. So in order to maximize this, let's say this v1 square we want to maximize, so this term we can, if d1 and alpha have the opposite sign, then this term, whatever we are having this minus sign, will go, and that will be positive. Okay, so what so to maximize v1 square, what we will use is so sine of alpha is equal to minus sine of d1. So this is just for convenience, or in order to avoid any numerical errors or amplification of the error. So to avoid this sign is chosen this way. So if we choose this opposite sign, so this term will be negative. So this term, if it is negative, so if this term is negative, this minus sign will be positive. So obviously we will get this term to be positive, and this square anyway there is there. So in order to avoid getting any negative values and going into the complex number, we can use this like if you use this way, it will solve this issue. Okay, so I will write what we have got. So v1 square is equal to half 1 minus d1 by alpha. Okay, so you can see this alpha is nothing but the magnitude of d itself. So fine. Okay, now what we will do is we will write this equation. So d2 plus 2 v1 v2 alpha into v1 v2 is equal to 0. So in this case we already have v1, so v2 is equal to minus d2 divided by 2 alpha v1, and this, if you see this minus alpha v1 is nothing but p, so we can write d2 by 2p. Okay, so in general we can write any vi is equal to minus di by 2p. Okay, so we got this v vector. Okay, so this is all the calculation we are supposed to know to compute the householder transformation. Okay, so I will summarize what we were doing. So we have the b vector, and this b vector has this initial component c and d. So this c part was composed of b1 b2 till br minus 1, and this d was having the part which is below, which is br to bn, and we were finding this u1 matrix into b such that after this multiplication we will get b1 b2 br minus 1. This br will be some alpha, and then after that it will be 0 0. Okay, so this u1, what we decided to be u. Okay, so u was I minus 2 w w transpose, and this w we have separated into like the 0, which will be of r minus 1 size vector, so it is of similar size as this one, and below that it will be v. Okay, and then in the components in this v we found out v1 is equal to, so you see that we have found out this v1. Okay, here, so v1 square was this one, v1 square is equal to half 1 minus d1 alpha. Okay, so d1 is what? So d1 is nothing but this vector is, so this part, so d vector is nothing but this part, so d1 d2 till dm, this is nothing but br to bn. Okay, so this d1 is already we know, which is br. Now this alpha we have found out before, so alpha is nothing but the magnitude of d because of this orthonormal nature of the matrix. Okay, okay, so alpha is nothing but magnitude of d. Okay, so this we can find out. This is, then v2 is equal to or vi, I will write general, vi is equal to minus di by 2p. Okay, now p has come, so p is what? P is v transpose d. Okay, so p is v transpose d. Okay, so this d matrix is we have, and this v matrix we are finding out, and that itself has this v transpose d, and we also have found out that this is the nothing but the p, p is nothing but minus v1 alpha. So I will remove this and write this p1 alpha, because that p is nothing but minus v1 alpha, minus v1 alpha. So you can see the procedure. So we will have, if we have this b matrix, we can get the d matrix, which has nothing but these components, and once we know this d component, we can compute the magnitude of this d matrix, d vector, which will be the alpha. Okay, so now with this we know the alpha value, we know the d1 value, which is nothing but this br, and it is nothing but the vector we are interested in, which is this one. Okay, so this d1 we have, so we will get v1. So once we have v1, we have alpha, so we'll get p1, and once we have p1, we can compute the next v values, because we know the d vector itself, which is already given. Okay, so I will quickly take one example of this, and I hope that you can get more clarity on this. So u is equal to, let's say, 1 3 4 3 1 2 4 2 1. Okay, so this is the matrix, and let's say we want to convert into tri-diagonal matrix. So let's say this is what we want to do. So to do this operation, so you can see that this first vector, let's say if we treat this as b, so for us b vector is 1 3 4, and what we want to transform this into 1, some value will come here instead of 3, so let's say we'll treat this as alpha, and this will be 0. Okay, so this is, so you can see, so this part is now for us is c, and this part is a d part. So in this d part we want to perform this action. Okay, so I will just write d is equal to 3 4, and then alpha, we saw that alpha is nothing but the magnitude of d. So magnitude of d will be square root of 3 square plus 4 square, which will be square root of 25, which will be 5. Okay, now it can be plus minus, so that sign we will decide based on the d value. And so you can see that this alpha value was there, and in order to maximize this v1, we have decided that we will take the sign of alpha, which is opposite of d1. So d1 is 3, so the alpha value we will choose opposite sign, which is minus 5. Okay, so that is fine. Then we'll find out v1 square is equal to half 1 minus d1 by alpha. Okay, so half 1 minus d1 is 3, alpha is minus 5. Okay, so v1 square is equal to half 1 plus 3 by 5. This is minus minus plus 1 plus 3 by 5, and that will be half 8 by 5. And if we take the square root, v1 is equal to let's say this is 4 by 5, so it will be 2 by square root of 5. Okay, so we got v1, and we will find out p is equal to minus alpha v1, that also we have derived here, p equal to minus v1 alpha. So minus alpha is what? Alpha is the magnitude of d vector, so magnitude is minus 5. So magnitude of this d vector is minus 5, is alpha, but now we have chose the sign based on the d, which is minus 5, and the v1 is already 2 by square root of 5, so that will be 2 square root 5. Okay, now what we will do is we will find the next value in the vector v2, which will be d2 by 2p. So d2 is this 4, and 2, and p is 2 square root of 5. So this 4 will get cancel, and it will be 5. Okay, so the vector v we have, which is v1 and v2, and this is size dimension is 2, because this d has 2 dimension. So we is supposed to be 2 dimensional, and it has the component 2 by root 5, and v2, which is 1 by root 5. Okay. And one more thing I will mention is, so this actually that transformation matrix that we will be using is, let's say, u1. So in that matrix, this w's involve this v vector. So that v vector we have found out. Okay, so in order to get this w vector, we are supposed to add these zeros till r minus 1. So you can see this r minus 1 is nothing but here till this. So whatever this part is there, so till that location we have to add 0, and this bottom part will be like whatever the remaining number of dimensions that will corresponds to the v. Okay, so this w we will write now. Actually it is like 2 minutes, I will complete this. It's almost done. Okay, so w that we are interested is in, w is equal to now 0 into times v. So this will be 0 2 square root of 5 and 1 square root of 5. There was one problem I think in assignment before, so that you can practice with this. So this w matrix we have now, u1 we have to find out, which will be I minus 2w transpose. So that I will write now directly. So it will be 1 0 0 0 0 minus 3 by 5 minus 4 by 5 okay. So this is the matrix we have, and you can see that this is the part which involves this is the part that is equivalent to identity matrix, because we don't want to change this one in this matrix, or this one we don't want to change. So if you don't want to change, we use this identity matrix, but it happened that it was 1 by 1, so it just showing 1 here. And then this part was actually I minus 2v transpose, this block, and that will modify this lower part of b, which is 3 4. Okay, so so if we multiply this u, so u1a, so in that case what will happen is, this 1 will be as it is, we'll get 0 here. But the thing is, the initial matrix was a symmetric matrix, but we will lose that symmetry, because this term, because this is 4, this 4 has gone, but this 4 has not gone. So in order to get the symmetric transformation, what we will be doing is, we'll multiply here also with this the transpose of this. So in this way we will get the zeros at the top also at this location. So now I will write this u transpose values, which will be minus 5 you can check values whether they are correct or not, but the main thing is what is the idea behind this. Okay, so this is the thing, and this is how we can convert, like use the householder transform to get the, let's say here in case we got the tridiagonal matrix, but you can read about this more, and then subsequently if we want to actually make it diagonal itself, how we can make that also you can think of. So in that case we have to, instead of making this 0, we have to make this also 0, So different ways you can be done, but this was the one example where we want to make this term specifically, which is 0, this corner element. So this is the tridiagonal matrix, so we want to convert that A into tridiagonal matrix, and this was the procedure. So this is if you see, this is the derivation, but that is big. But if you see the process, it is not that big. So in 3 slides we have covered it, but the logic behind that transformation is this one. So first step in the transformation was like how this householder matrix came. Was it came because of this reflection. uh, so we start with the reflection, so we derived this. So in this case, we show that about this plane we want to reflect, which has the w as the normal vector, and we found out how to get the reflection, and then we found out the reflection matrix. So this was the matrix which was reflecting the u, and that was the householder matrix. So this is how that's how it takes this form, I minus 2w w transpose. Okay, so once we have this form, we saw that if we have the for the rotational matrix, we saw it is orthonormal. It means that it has the each one has the magnitude, sorry, it should be 1. So each one has the magnitude 1. So if we take the r transpose r, it will be identity matrix, and that is nothing but the orthonormal matrix. So for orthonormal matrix, the magnitude of vector doesn't change. Okay, so the magnitude doesn't change. So that was the only thing I want to tell about this orthonormal matrix. So then we started with the householder transformation, where we have, let's say, some vector b, and we want to transform it such that it's all the terms below this rth value was 0. So till this 1 to first r minus terms will be as it is, the rth term will get modified, and below that it will be 0. So if we use this u matrix and operate it on b, so it will be, so these terms will be unchanged, this term will be alpha, and this all terms will be 0. So that's what we wanted. And then we started with this householder matrix, and then to keep this c unchanged, we use this identity matrix here, and then we used only householder transformation here, like which is correspond to this d part. So in this d part we have used this u, and that's how this ud has come here, and this ud will achieve this task where, so this task alpha 0 0 will be achieved by this u into d. So we want to find this u. So now this u will have this u will be I minus 2 v transpose. So this v is nothing but the vector. Okay, so v is the vector, and then this elements of v will be v1 to vm, and that's elements we did some derivation, and then we found out that the v will have this element, v1 will be like this, and any ith element will be of this form. Okay, so that was the that's how we found out this u matrix I minus 2w w transpose, where w was 0, which was r minus 1 size, and then it was having the lower element was v. So that's what we have, this derivation all is dealing with. Then we saw the example how to convert this matrix into tridiagonal matrix, where this b so if you want to convert this tridiagonal, we want 0 at this location. So we put this, like this is the matrix, so we put this mark here. So we are treating this c as a, so this 1 as c, and then 3 4 as d vector, and then we did the further calculations to get this. So I hope this is procedure is clear. You can try the derivation, it is not difficult, but it is lengthy procedure. Yeah, I hope this is clear. Okay, Chandan, did you got this?
Yes, sir.
Okay.
Yes, yes, certainly, yes, sir. Like if I go through once and if I work out, it will be clear now.
Okay, okay. Yeah. Okay, then we'll stop here. Okay.
Thank you, sir.
Yeah. Okay, then. Bye.
Bye, sir.